All right, 203. Let's get started. And feel free to pop in with questions if you guys have any. You can just interrupt me. It's fine. All right. So in terms of topics, what I want to focus on is just simply like what are power electronics? Where do we use them? Just for a brief introductory. Then go on to some of the building blocks that we use for that, and then the hardware design for buck converters in terms of part selection and more real life. So just going on to what power electronics are, it's basically anything solid state, meaning non-moving part. So that would be like your MOSFETs and such versus a moving part example might be like a motor where you can use motor to generate power, but it's not solid state, there's motion to it. And then anything that's really converting power, again, solid state though. So you can see the buck converter. This is something you might see a lot. Makers love these things. They're like $1 or so. And these are just very low end buck converters. And also you have your PFC rectifier. So that's power factor correction rectifier. And that is for like more of a phone charger. And I'm sure you guys have noticed like over the time you stuck in those wall warts and they're shrinking smaller and smaller. And the real reason why is there's a transformer in there and they're getting that transformer smaller because they're switching faster. So the power electronics inside are able to go quicker and quicker. And as a result, they need less and less copper rammed into a little plastic box. Then of course, last motor controller. We'll show off a photo of that next week. No need to show it off this week. So now just going to like, where do the power electronics really exist in the car? In terms of things that are pure power electronics, like a lot of other things in the car even have power electronics built in, but it's not the main part. Like the BMS has a buck converter on it, but that's not really the real show. But in terms of crucial power electronics, you have the contact driver. So this is more of a control thing. It controls power going in or out, but it's not really converting voltage levels. So it's either like, it's like an electrical switch. So either the contactor gets power to open up or it doesn't, and then it will close. Moving on, we have the power distribution board Dimitri designed. And that's more, again, kind of the switch for control. It's not very much converting voltage levels or current levels, but it's instead just being a switch. So it's watching very closely all the currents flowing through the car. And in the case that there is an overcurrent within microseconds, it can cut it off. Versus when you have something like a fuse, which is a thermal device, you're waiting for that fuse to get hot and melt. You're going to lose power just through the fuse in general a lot more. And also it's going to take milliseconds, if not entire seconds, for the fuse to break. And by then all your shit is broken. So fuses are actually kind of too slow. And we use them more as like a last resort where we know for sure it'll work no matter what, but it's not the best solution. And then now moving to more of the converters. So we have the multi-phase buck that Alex designed. This is just a bunch of buck converters taped together in a clever way. We can have a lecture about that if people are interested, but at the moment, just a little too much complexity. Then we have the headlight and taillight bucks. So that's taking down our middle voltage rail of 12 volts and stepping down to 5 volts to feed the LEDs. And then we also have our BLDC motor driver, which is actually more like a current source in a clever way. And we'll talk about that next week, where again, it's converting this voltage source into a current source. So just going on the basic parts, I have no clue how 110's going for some people, because I'm sure what are they just about stop teaching there? They're going to go online, Prairie Learn, all that fun. So starting with just basic resistors. So the two governing equations we really care about is V equals IR and P equals I squared R. You've seen other variations of P probably where it's like V squared over R and all these different things. They all equal the same thing, just using Ohm's law, you can swap between. And really the main use for like the simplistic thing in power is you just use them to limit current. Moving on to capacitors, you have your capacitance times change in voltage over time is your current. So this is basically just conservation of charge. The more charge you have in a capacitor, the higher the voltage. That's all that's really saying. So, and then also the ideal capacitor has zero power. Go ahead. All right, I'll keep going. So really the main use for capacitors is we want to store a small amount of energy, and we use them to resist changes in voltage. In terms of schematic symbols, you see the one, can you guys see my mouse or no?
No, yeah.
I'll use this little draw thing just in case. Anyways, so you see this capacitor symbol here. This is a non-polar capacitor. So either side can be the positive or negative, or you can switch in between. So these are usually ceramic capacitors or film capacitors. And then here you have the polar capacitors. these are usually electrolytic capacitors or tantalum capacitors. So these capacitors, you can't have a negative charge on the positive side, because what will happen is they rely on a kind of a rust layer to be that very thin wall that isolates the two conductive surfaces. And if you put a reverse voltage across it, you will electrolyze away that rust wall, and it'll turn into a short circuit, and it'll just explode. So yeah, you don't want to do that. Make sure you pay attention. So like I said, electrolytics, tantalum, you got to be careful. They're polar. Ceramics, you can do whatever you want in terms of voltage across either side. They don't care. All right, and then let me clear that. Moving on to inductors. So inductors, L di dt equals V. Not really that intuitive of a thing, but all that's saying is the change in current through an inductor is the voltage divided by the inductance. So that means that in an ideal inductor, if I put 1 volt across it, there's no limit on the current going through it. It will look like a short circuit in the long term, but in the very brief start of the circuit, you have no current going through it, and it takes time for that current to change. So it's going to look like an open circuit. So really, what we use the inductor for is to resist change in current. We just use it to kind of hold current steady if we have an up and down, so we can average it out. And again, this is storing energy, versus the capacitor stores energy in the electric fields. An inductor instead stores energy in the magnetic field. Okay, all right, no more drawing things. Again, my computer angry. All right, the last kind of main part we're going to hit on is the MOSFET switches. So for some reason, I accidentally left in LDIT, but anyways, moving on to, again, an ideal FET has 0 losses, but we all know that's not really true. And it can only block current flow in one direction. I just want to kind of point this out because this was a confusion for me earlier. So if you have a voltage source, let's say here, where we have a plus here and a minus here, and then we connect it here. So even if the FET is in an off state, it won't matter because the current will just flow through this body diode and close the loop. It can only block current this way in its off state, because that body diode won't let it through. And then if this is off, it's not getting through. Additionally, what I want to point out is how conduction works. So also because of this, many people believe that the FET, when it's on, is a one-way street. So if it's conducting, it won't let you go backwards. You can only go this way. And then additionally, they think, okay, I'm gonna have this really lossy path through a diode, but that also isn't true. When this is conducting, power can go both ways through the high conductive area. It's basically just a wire at that point. So you can have current both ways and through the low loss path of a FET. So how do we even control this FET is on an on or off stage as more of a switch? That's by changing the gate voltage versus the source. So that's called oftentimes VGS in short. And in terms of how this controls it, there are 2 types. You have N channels, which is the most commonly used. And N channels will turn on when the gate voltage, gate to source, is higher than roughly 3 volts in most FETs. And then you have the other side, which are the P channels, which are the opposite, where it's on when the difference between gate and source is 0 or negative, and it's off when it's above 3 volts. And the reason why people use P channels is more of a lazy way of controlling the high side MOSFET without creating a voltage higher than your inputs. However, this really isn't used because of some of the more in-depth parts of how these devices work. The NFET relies on the ability of electrons to travel through it. And electrons are very mobile, so you have a low RDS. However, P-channel FETs rely on the travels of holes, which aren't as mobile. As a result, you have a higher RDS. So really, in a nutshell, if you use P-channels, you're going to have more loss. So it's just a lazy way of not putting in the extra work of using 2 NFETs. And it's really just a poor idea unless you're really trying to cut costs. And for car teams, we really aren't. We're trying to get performance. All right. So moving on to the really simple example of an LED that we want to run. This is probably how everyone started, where we have an LED and we have 12 volts and we want to give 3 volts at 20 milliamps. So starting off with the naive way of using a resistor, we can simply solve for V equals IR to lower the 12 to 3. So we say 12 minus 3 equals R times our current through the LED, and we need 450 ohms. Now, the issue is for efficiency. So we have our power out over power in, simple efficiency, right? And in this case, we have 20 milliamps times the 3 volts, so that's our power out. And then our power in is that same 20 milliamps times our voltage in, which is our 12 volts. So we get 25% efficiency. Not really the best. And if you do this with a linear regulator, it's going to do the same thing. So again, 25% efficiency. So we want to do better than that. So instead, we just PWM instead to get an average of 3 volts. So only a quarter of the time do we give it the full 12 volts. And then for the rest of the time, we give it 0 volts. So now we have 100% efficiency because we have 20 millivolts times our 3 volts out over our 20 milliamps times our 12 volts times a quarter, which is our duty cycle of giving it power. Well, now we have 100%. So that's great. However, we both know this isn't really going to work because we want the average to be true, but we're still getting these pulses. So you're putting 12 volts against the LED, and then it's going to drop down to 0. But during that 12 volts, you're going to get huge current spikes that will just blow the LED right out. You're going to see a flash, and then it's going to go dark and never work again. So we want to figure out how to solve that. So basically, we're going to kind of band-aid that over with a filter. And the filter is going to average it for us. So I want to get more into talking about how we design this filter. So there's 3 main parts to the filter. One is our input here. This is our input capacitor, and this helps us prevent any large-scale ripple from across the RV in, because there are parasitics here. So our battery isn't perfect. If you try pulling 60 amps out of the battery, it's going to take time for the battery to ramp up its current to reach you due to some inductance in the lines, which is again going to resist that change in current. So we need a local power supply that's tiny but can give us that power real fast. And that's the point of your input capacitor. Next is our inductor. So we don't want the FETs to spike high current and then go 0 for both ends, like either the high side or the low side. That'd be an issue. So we use this inductor to resist that change in current to smooth it out. And then last, we have our output capacitor. So that inductor is still going to have up and downs in current, which means our LED would experience up and downs in current, which would create voltage spikes. So we use that capacitor to kind of hold that temporary charge. If we're in a down and we have a lack of current, that capacitor can kind of give us a little extra energy and make up for that. Then if we're an up, that capacitor can eat a little bit of that extra energy and store it for later. So that's really the idea behind the filters. So we're going to start with an inductor and go into more of the math now of how we solve for this. So the idea is you kind of charge up the inductor when you have the high switch closed. So now we have V in minus V out. That's the voltage across the inductor. So we're going to start seeing our current start to rise. And you can see this in the IA version of the drawing right here, where this is where we're kind of starting. And then as we conduct more and more, that I is going to slowly climb. And it's basically a straight line across. So that's not even like an approximation. If you take real measurements, it's just about constant. And then on the other side, now that we're done with this, we're going to switch modes to this because now we have too much current. So we're going to start going down again. And we're going to cash in on that energy we've stored in that magnetic field. And that's going to be basically V out, 0 minus V out is now your voltage across your inductor. So you have a negative voltage. So now your change in current will be negative. Hence the negative slope and it's going to climb down. Add them all together and you get this as your output. So this is called our ripple current. So right here in the middle, this is our actual like I out. However, we're going to kind of bounce around that, and that's going to be our ripple range right here to here. So that's the first thing we want to decide is how big we want that ripple to be. This is kind of arbitrary. So we don't really care about a ripple current. We care more about a ripple voltage, but we need to solve for a ripple current to get that. And because you have multiple variables, you kind of make an arbitrary decision on one. So usually the rule of thumb to kind of get like a reasonable values for both your inductor and then later on your capacitor is to do about 20 to 40% of your rated output should be your ripple. So for example, if we had a 20 amp buck converter, we'd want to target a ripple current of about 6 amps. And the way that you can solve for what your inductor should be is you plug in for your ripple current, multiply it by FSW. So this is your switching frequency. And this is also another arbitrary value where the designer needs to figure out what they want. The bigger FSW goes, the more losses you're going to have. But the smaller you go, as you see, because it's on the bottom, you're going to need bigger inductors. So you have to waste a bunch of money on getting bigger hunks of metal and copper in there and iron for your ferrite core. So that's going to add weight to your vehicle. Also, it's going to take up a lot more board space because it's a very large physical object. So it's all about a balance whenever you're designing these things. Usually for lower power things, you go lower switching. So if we're talking about our motor controller, we might only do 20,000 for our switching frequency. But if we're talking about our little buck converters that might supply like half an amp, where losses aren't as big of a deal, we might push it up to 500,000 for our switching frequency. So it's all about kind of where your power range is. And as you go higher power, you're going to slow down for your frequency. So we've picked this value, we've picked this value. Now we just need a D to solve for L. And D is very simple. It's V out over V in. Now, let's say you're designing a general buck converter and you don't know what the V out or V in is because it could be a range. Then let's just pick worst case, which is going to be 0.5, which will give us a total here of 0.25. There's no way to get higher than that up top. So with all those values, you can solve for L pretty simply. Any questions there? Cool. All right, moving on. Output capacitor. So now this is the other part of our output filter. And we're going to start now with a target ripple voltage. Again, this is somewhat arbitrary, but this is actually a lot more defined, luckily, for applications. So it all depends what you want to do. If I'm doing like a light bulb or a gate driver, something where I really don't care about how clean the power is I feed it, and it doesn't really care either, we can give it probably about a volt of ripple and it's going to be fine. So that's what I would suggest there. However, when you have something like microcontrollers and these digital processors where they're very sensitive to noise, you got to be more careful and give cleaner power. So there you want to target less than 100 millivolts instead. So it's all about knowing what your target application is. Always err on the safe side for this thing. There's no such thing as too clean of power. It's always a better thing. You might give up a little of efficiency, but you're going to prevent yourself from having a headache of having dirty power and then it causing issues down the road. And then you not knowing, is it my buck converter or is it the device I'm working with now? So always err on the safe side for that. And again, a simple equation that we use to solve this is we're going to take that ripple current we talked about in the last slide. We're going to bring that over here now. And then we're going to divide that by 8 times our ripple voltage. So that's your delta V out here. And then again, the switching frequency we had from last slide as well. And all this is really taken into account is as we go up and down versus our target here is this, in this case, we have our excess current going in to our capacitor. So that's going to make the capacitor go up in voltage. And then we have this lack of current here where we're below our target I out, and that's going to make our voltage sag. So the larger the capacitor is, the less that voltage differential will be, because let's go back here. Like we talked about before for capacitors, it's going to be that change in voltage is going to be I over C. So if your C is very large, your change in voltage will be quite small. And that's really our target there. And again, it's all about a balance of you can go nuts with this and make it 0, but you're going to have such large values that it's going to be very unpractical when you're actually trying to build this device physically. All right, now moving on to input capacitors. This is often overlooked, and it's one of the less talked about things in the classes at U of I, but this is really critical. So I want to say it was last year that we had very small input capacitors, and we didn't know why. Things just weren't working right. Sometimes the relays would turn off, and later what we figured out was it was because our voltage rail, our input rail, had near 0 capacitance, and we had just the bare minimum to prevent anything from exploding. And as a result, that rail was swinging up and down by 10, 15 volts. So everything that was getting power was getting these massive spikes both ways. And like we just talked about, that's going to mess up your digital electronics. So we want to make sure we keep a cleaner power rail there. Usually a common target for this is roughly 10% of your input voltage. So we have a 50 volt bus for our car. We're going to do about a 5 volt ripple target there. And again, for here, it's similar to the last equation where you have your D times 1 minus D times I out, and I out being the current out of the buck converter. So that's your low voltage current. Don't worry about I in. That's not part of this equation because I in is always smaller by definition of a buck converter. And if you use your I in here, you're going to get a wrong value for C. And it's actually going to be too small, so you're going to have ripple issues in the future. And then again, bringing back that other, for this delta, this is delta VN. That is different than your delta V out. So I just want to mark that. That's why they actually have different subscripts here. So again, this is your 10% value versus the other one is an application-specific value. And then last, switching frequency. Again, this is the same one from the inductor equation and the output capacitor equation. And then again, for D, V out over V in next year, use worst case. Always use worst case when you're designing things, because if you do that and you don't have worst case, you're going to be fine. So now I want to move into more of some real life topics. So I went over a lot of theory, and I went over it quickly because you can always look in the papers. I'm going to share resources into where these are derived, but oftentimes, I don't know, for me, when I'm usually learning a subject for the first time, I'm not too interested in where they're deriving these parts from, but more kind of interested in, all right, how do I solve these problems? And here's some things that will catch you if you just plug into those blindly. The first thing we're going to talk about is capacitors. And there's really two types of capacitors. There's the electrolytic and polymer caps, and these are really big capacitors. They're the big round cylinders you see on boards. They have very large capacitance. They're pretty cheap, but the issue is they're really high in parasitics. And when I say parasitics, I'm talking about these guys right here, which is ESR and ESL. And so you're like, oh, a capacitor is just this, but really it has this internal resistance into it, like everything does, and it also has this internal inductance. So the point of the capacitor is we want it to put up burst currents and to take inverse current. But because of these higher values here, if they get too large, it can't really take in that burst current because that inductor is going to resist that change in current to go in and out. So now our capacitor is going to kind of lag and we're going to get instability. We'll get that ripple that we're trying to prevent with the capacitor. On the other side, we have our ceramic capacitors here. And the issue with ceramics is they're quite small. So this value isn't usually what we want. They're also pretty expensive for the capacitance. But the nice thing is these are just about near zero. You really don't have to worry about ESR and ESL with ceramic capacitors. It's just about perfect. And that's kind of demonstrated here. So ESR, this is a constant. Let me clean that up real quick. So ESR, no matter what speed you're switching at, this is going to stay the same. Voltage across a resistor is always going to be IR. However, voltage across an inductor is not. So if those in 210 will know the J omega L equation, and that's your impedance of an inductor. And for our voltage, it's going to be V equals Z times I. So as a result, with W being frequency here, we're going to see on this chart here that the ones with high parasitics, they're not really very good at being low ESL and ESR. They can't really handle that burst current because their impedance stays super duper high at these higher frequencies. Versus if you look at some of the ceramic capacitors, as frequency increases, they do better and better and better. So these aren't issues. And that's why when we're doing these high switching frequency things, especially when we talked about doing like a 500 kilohertz switching for some of our smaller buck converters, it's all about your ceramic capacitors. The electrolytics are useless. They might as well not be there. They don't do anything. Versus if we're talking about very large objects, such as the motor controller that we're talking about right here, you can see that we have really large electrolytic capacitors. And we do have our ceramics for those quick little bursts of current. Because we're talking about 20 kilohertz, it's very important that we have these large storage tanks because you need to provide that localized energy for a long time. All right, any questions there? Okay, let's clear that and then move on. So let's do a little bit more of a deep dive into these capacitors and kind of talk about some of the data sheets behind them. So we already rambled a lot about high parasitics, and this has other direct effects for the part itself. One is limited ripple current. So because you have that ESR in there, it actually will generate heat inside the capacitor as you use them. So you have your I squared R loss inside that capacitor. So if we look at right here, this is those big kind of storage tanks I just mentioned for the motor controller. They have a massive 1.6 millifarad capacitance, and they have a rating of 5.66 amps. So if we plug into, if we use this capacitor at rated value, you're going to get 0.66 watts of loss per capacitor. So this is all heat you need to get rid of. You also need to be careful here because we don't really think about a watt or two as a lot, but actually a couple watts builds up a lot of heat very quick on capacitors and other components that aren't heat sinked, because the heat doesn't really go anywhere. It just builds up and up. So you have to be careful and make sure that you don't burn them up. So what happens is, we've had this issue too before where we didn't pay close attention to this ripple current and we broke the specification. So let's say we use 10 amps here instead. Well, now this is going to get a lot bigger. So we've just about doubled what the ripple current rating is, but that means we have 4 times the power loss because you have I squared R, and the R isn't changed, and we doubled I, so now we have 4 times loss. So as a result, your capacitor is going to overheat, and these things explode spectacularly, excuse me, when they go, and it will look like there's a fire in the car. In fact, I want to say 2 years ago when we were first experimenting with motor control, we tried using one of these as a snubber. We put a lot of ripple through it, and it exploded, and we thought the battery caught fire because there was so much smoke pouring out of the back of the car. Really, it was this little capacitor just went. Okay, and then also, like we talked about last time, this capacitance is going to fall with frequency, and really it's not actually the capacitor, that part that's falling, but it's this ESL that's getting in the way that makes it look like that capacitor isn't there as much, because it can't do as much because we're limiting its ability to take in current in and out. So that's it for electrolytics. Moving on now to ceramic capacitors. So I'm more of a ceramic fanboy, obviously. And the only issue, like we talked about, is cost, and they're not as large, but they still have some downsides too. So first, starting with the upsides, they're really great at ripple current. Do not worry about ripple current ceramics. It does not matter. Same thing for loss, near zero. Don't worry about it. It's negligible. It's fine. The only things where you need to be careful ceramics, and this was a discovery for us, is something called DC biased. So what happens is DC biased is just a voltage across a ceramic capacitor that's DC. So for electrolytics, if I have 48 volts across them, it's going to keep the same capacitance as if I had 0 volts across it. Ceramic capacitors don't do that. And as you see in the chart here, as you get more and more voltage across the capacitance goes down. So this has some weird like electric field effect things and how the ceramics behave and such behind it. You don't really need to worry much about it besides this kind of generic thing where you need to be aware of what voltage am I giving across this, and understand that because, for example, our motor controller, we have 48 volts across our ceramic capacitors, most of those capacitances are half of what they're rated at. So our 10 microfarad capacitors are really more like 5 to 4. So it's something to be aware of when you're selecting parts. And there are ways that we can kind of limit this effects, and that is physically use bigger capacitors. So like you saw here, these capacitors, if I can interact with this, are massive. These are 2220 capacitors versus before we were using these tiny 0805s and 1206 capacitors, and we've upgraded that to help deal with that DC biased effect, where just simply by having more ceramic there, the DC biased effect will go down. Oh, sorry, just realized that there's a chat. Oh, sorry. So Skylar, I'm not sure. Okay, just ask that a little bit ago. Which values are you talking about? And you guys are welcome to speak too. You don't have to just use the chat.
It depends on the board. Like, it depends what you need to design. It's like,
Yeah, so I'll run back to you at the end, and then if you have a mic too, that'll help. We're just about going to be, we're done with the capacitors, and now we're going to hit inductors. We're going to round out with switches, and then we can do Q&A afterwards. Yeah, we'll do that. We're talking about school of thought at the end. Cool. All right, so moving on now to real life inductors. These are way easier, guys, so you can be a lot less concerned about them. So real life inductors, we don't care. There is parasitic capacitance. It doesn't matter. It's like near zero. The only thing you have to really worry about for real life inductors is their natural resistance. So for real life inductors, our issue is that they will naturally just kind of build a peak because it's literally just a bunch of copper. And there's also some other losses with ferromagnetics where the switching creates field losses of like from hysteresis and such. You don't have to worry about those. When you buy inductors, they're small. They don't matter. All we care about is our I squared R from our copper. So what we want to talk about here is we want to watch out for our current limit. So here's actually an inductor we use for some low current switching. And we can see here that it is about 0.3 of an ohm of resistance, and it has a max DC current rating of 620. So you could plug in for I squared R there, and I did, and it looks like you get 1/3 of a watt loss from your inductor. So these are just things to think about. So when you're trying to choose an inductor, let's say of 68 microhenry, you can use really tiny inductors, but they're going to have very high resistances, and as a result, you can't put as much current through them because your I squared R losses will get too big and you're going to start burning things on your board. Now, on the other hand, you don't want a large inductor either because A, it's obnoxious, so it takes up board space you don't want, and it adds weight to the car and it adds cost as well. So like everything here, it's a balancing act. And what really sucks, I really kind of hate some of these things, is there's no right answer. There's a whole spectrum of what do you want. So we're talking about that and the design of philosophies at the end. And it is kind of an art and you get a feel for it. There's no equation I can give you though. It's like, here's the exact inductor size you should use. Here's how much current you should have. I can talk to you about the minimums and then we can talk about the efficiency calculations for that. But that's really it for it. And then the other thing I want to mention here is something called saturation. So cleaning up all those drawings real quick, you notice there's actually 2 rated currents here. There's the 800 milliamp hour, and that's what your saturation current. And then there's the 620 milliamp, which is your DC rating. So the DC rating this is how much heat we can have. This is how much I squared R losses we can have before we run into issues. The saturation current is something different, and that's shown here in this graph, which is an inductor, like everything, is not perfect. And as you start putting more and more current through it, its inductance starts to fall. And really, it's this knee that you're watching out for. So once you break this knee, you're losing your inductance quite rapidly. And that's where they talk about saturation, is they're kind of marking a spot where it's like, stop here, else you're going to hit this knee, and your inductor turns into a wire. So when that happens, we might have this little ripple current here, but the moment we start breaking that inductor limit, you're going to have this ripple current going up, and then you break it, and you're going to shoot up super high, and then you're going to shoot down really low, and then you're going to go back to normal again. This is what happens when you're going to break that saturation. So it's very important that you don't. Now, why not just always follow just look at this, and as long as we're below our DC current, we're not going to have issues? Well, we talked about ripple current, right? So you have your DC part of your buck converter, which is sending out, let's say, I out. And we have our AC part, which is that ripple current we mentioned. You need to add the peak of the ripple with the DC value to make sure that is below your saturation. We don't care about the ripple for our max DC current. That's going to cancel out. This is a AC component, so we don't really care. But for saturation, we do. Because the moment we violate that, we're going to start breaking that knee, and our current's going to spike very high. So even though it looks like you're going to be slightly above, because as you fall down that knee, your current's going to go up and up and up very rapidly. So you don't want that. All right. Now moving on to our last topic in real life, which is our MOSFETs. So let's talk about kind of our first VDS rating. When you're choosing a MOSFET, one of the first things I sort by is VDS. And the rule of thumb that Professor Banerjee teaches at U of I that I like is choose a rating that is 2 times whatever you're feeding it. So for our cars motor controllers, we use 50 volts in. Our MOSFETs are rated for 100. And the reason why you do this is as you turn these on and off, you're going to get spikes that can be very, very large depending on how aggressive you are. And if your VDS isn't large enough, those spikes will just destroy your FET and turn it into a short circuit. If you have 2 FETs like in a half bridge and they both fail, you get a short from battery to ground. So you want to make sure these are large enough because you get one shot. And the moment you break it, the FET is just about done and it's unrecoverable. So you have to replace the FET at least, and you might even take more parts of your board with it. So always at least do ×2. The main reason why people are kind of hesitant to choose these larger VDS ratings, because you're like, okay, why not just use ×10, is because as VDS goes up, so does your resistance. So again, it's all the balance here. So you kind of want to do about ×2. If you get really good at layout, you can kind of take that back a little bit. Maybe I've seen PhDs use like times like 1/2 instead, but you always want to make sure you have that headway. And then moving on now to, we talked about pretending that a FET is lossless. Obviously, it's not really. And there's 2 types of losses. One is our switching losses, which I have another slide on. And then the other one is the conduction losses. And that one's really simple. That's just your I²R through your FET. And know that this isn't I out, but it's actually going to be I through the FET as long as the FET's on. So if we're talking about our high side FET in our buck converter, that FET will experience IR times D because it's going to be that duty cycle. How long are we actually using that FET? And once that FET's off, we don't have that conduction loss through it. And the bottom FET's going to be 1 minus D times your I²R. Because the bottom FET is on for all the time that our top side isn't. So you're actually distributing those losses between the two. And that doesn't help you reduce conduction losses, but what that does help you do is move the heat from one FET. Now you have the heat coming out of both FETs. So the only thing you want to note there is if your D is very large or very small, one FET is still going to take all the heat. And then another nice rule of thumb that Professor Banerjee from 464 talks about is the importance of getting your switching losses to roughly your conduction losses. This isn't like a vital thing where it's like, oh, you must do this or something explode. But this is a rule of thumb to help balance your losses. Because like we talked about here, we can make VDS very large, which is going to increase our RDS, which means our conduction losses will go up. But we can use that high VDS to switch more aggressively to lower the switching losses, and I'll get into that. However, now you're going to get this imbalance, and kind of as you get more aggressive with your VDS, your I²R losses are going to overtake. And on the other side, if you get your I²R losses too low, you can't switch on and off as quickly. Your switching losses will go up. So by targeting during your design process for them to be about the same, you can save a lot of hassle versus trying to optimize every little thing. Because again, like we're making assumptions here, and we're doing a lot of rules of thumb because you can't optimize this problem. It's too complex. You can't go through all the Mauser catalog and check every FET and see which one's going to get the best result. So we can kind of make these assumptions. We might give up like 1% of an improvement on the design, but that's okay. All right, and now talking about switching losses. So right here, this is the equation that governs switching losses. And what switching losses are is we like to think of the current through the FET as, you know, just our I out and then it goes straight to 0. But really, it's kind of our I out and then it kind of turns off slowly. So this is our current. And then if we draw out voltage here, so the voltage across the FET when the FET is on is 0. Then when the FET is off, it shoots up. So again, this is the ideal. If you multiply these two together, you're going to get 0 the whole way across. However, in real life, it is 0 across most of the time. But as that FET turns off, the voltage across is going to rise. And here, we are not getting a 0 loss, but we actually have a positive number, which means we're going to start getting those switching losses. So our goal here is to make this as steep as possible, because that's going to lower the time that we're having that loss there. So a lot of people will be like, okay, why not make IG huge? And we just kind of talked about this. The faster you switch, the more spikes you're going to get. And those spikes are going to break your FET. So you can make these larger VDSs so you can handle these larger spikes, but then you're just offloading your losses from switching to conduction. Usually a rule of thumb that I like to target is about 300 nanoseconds is kind of a safe bet for your turn on times. And I can post more links into that. I want to limit how much I ramble about every little part of this kind of topic because it's very complex and it can't be all covered in one go. So this is why this is kind of like, you can't just get this to 0 here. Next, why not make this super duper low, right? That's another way we can reduce our power losses, but you can't do this. But like we talked about for the L selection and the C selection for our filter, our switching is on the bottom of our fraction, which means as this gets small, L and C get large. So you can reduce losses there, but now you're wasting a ton of board space and a ton of money on these massive parts. And also those larger L inductors, they're going to have more resistance. So again, you're taking your switching losses and just hiding them in your conduction. So you have to be careful there. There's no way to really zero this out. And last is, can we just find a FET that has this low gate charge here? So this part of the fraction is saying this is how long it takes us to turn the FET on and off, with IG being the current flowing into the FET, and QGS and QGD, this is just IG in a nutshell. That's just the gate capacitance. So we can try making this value low, but what happens again, you hide it in the conduction losses. FETs that have the lower RDSs in general have the higher gate charges just in nature. That's how the silicon works. So it's always a balance here, which is why we talked about that rule of thumb earlier. So you kind of go back and forth looking through catalogs. You're going to pick, let's say, a target like resistance. So I know what I want my switching losses to be, or I choose a target efficiency. Let's say I want 97% efficiency for my rated power. So I will solve for how much power I can lose. So that's going to be 3% times, let's say, 10 watts out. So I'm going to plan on 3 watts of loss. Now what I'm going to do is solve for the I squared R I need to get that 3 watts over 2. So now I have my target RDS. And then from there, I can start evaluating my switching losses and playing with different values to get this. So I might look at different FETs that have these low gate charges to balance it while still meeting my RDS requirement. And then on the other side, I might kind of tune my switching frequency. So I might raise that or lower that to hit my target. And then last is I can get more aggressive with my gate current. Again, be careful with this. It's kind of an art, and usually we're actually having many different resistor values to decide what our IG is. So like we talked about here, the IG is just the voltage you're driving the FET with over the gate resistance. So we have a bunch of values here, and we kind of play around with it and see which one doesn't explode. So it can be incremental to a point there. So that's really switching losses in a nutshell. Moving on now. So the last part about FETs is gate driving. So a gate driver, you might have in 110 played around a little bit where you just send a PWM straight into a MOSFET and it turns on and off and it's real great. It's super simple. But that's not how real life works because we have 2 MOSFETs and one of them is a problem child, being this one here. And the issue with the high side FET, as it's called, is that the source voltage here is changing. So when the bottom FET is on, this is connected to ground, right? So our gate to source is just whatever gate is. However, when this FET is on, this one is now, for a motor controller, for example, connected to 48 volts, which means if we want to turn on, if we want to keep this FET on, it needs to keep going up in voltage until it's, example, we want to target 12 volts above for gate to source. This needs to be 60 volts. So now we actually need to somehow create a voltage higher than we even have access to because the battery is only giving us 48. And that's where our bootstrap capacitor comes on. And the idea behind this is first we're going to kind of pretend that this is in an off state. So this is at ground. And here, as you see, we have 12 volts. So this is going to flow through this diode and charge up this capacitor to 12 volts. So great, now that's all charged. We got 12 volts right here across it. And if we look, that's 12 volts, not from the top of the capacitor to ground, but the top of the capacitor to our switch node here. So, excuse me, as we start to turn on this FET and this voltage starts to go up, so does the voltage here that goes across the capacitor. So this, let's say, goes to 20 volts during halfway through our turn on. This is at 20. So this is at 32. So we're still able to keep this FET in our on state from gate to source being 12 volts. So that's kind of the ideology behind these bootstrap setups. And when you're really designing these, this is, for example, the one we use on the motor controller. This is actually straight out of their example design. So it's not in the end super hard. They can give suggested values. And in general, what TI suggests is that bootstrap capacitor that that arrow points to should be 10 times whatever the MOSFET capacitance is, and that's in the MOSFET data sheet. So there's a gate capacitance, let's say, is in our case for some of our motor controller FETs, it's 1 microfarad or 0.1 microfarad. So this value is 1 microfarad. Also, we again need that decoupling capacitance because this is also in a way kind of a switch node as well. So you need that local energy there. So when this thing goes low, you can dump all the power in here through that diode very quickly into here because this is going to have resistance. It's going to have inductance. It's not going to give you that power quick enough. So you need that local capacitor to give you that energy. And again, we don't want that one. This is giving up energy. So it's going down in voltage as you dump that energy. So we want to make sure it's big enough that it doesn't go too low. So that's where that rule of thumb comes again. This should be 10 times what this one is. So this would be, for our case, 10 microfarads. And basically, in a nutshell, that's how you do a bootstrap capacitor. Or yeah, a bootstrap driver. They do have other drivers that are more clever that use things called charge pumps. They're not very common. They don't make a lot of sense, and you get very little gain. The only difference between a charge pump one and this design is the charge pump uses a separate switch to kind of do that up and down that we talked about here that has this float. And the only reason you want that is because this capacitor is going to sag over time. So this one has like a little leak across it, right? So you're going to leak a tad bit of power out of your gate here to your source. So this will slowly go down in voltage over time, which means you cannot do D equals 1. You cannot have a 100% duty cycle. You can only, let's say, do D equals 0.98, which is pretty good. You really shouldn't need to go higher. So that's the only reason why you might see some people promise 100% duty cycle charge pumps. They're not really needed. They rarely make sense. I would not suggest worrying about them. All right, last, kind of we talked a lot about our buck converter, and then you might also see some linear regulators baked in. I just wanted to quickly at the end touch on why we use one or the other. So the reason why people like linear regulators, they're really simple, they're really low noise. So like we talked about, you have all this noise here, you have all this switching. This guy gets in clean power, he puts out clean power slightly less. And you know, because of that, he's also very low cost. If you look, there's very little parts here. There's 2 capacitors, and this thing can cost less than $1. But our issue is we have very low efficiency because this is just literally burning off that extra energy. You're just getting heat pouring out of these things where it's going to be V out over V in. So if we want to make a 3.3 volt rail off our car's 48 volt battery, you're going to get like single digit percentages for your efficiency. That's really bad. However, if we're instead dropping down from 5 volts to 3 volts, well, that's pretty acceptable. And also what you want to think about too is how much power are you really drawing? So right here, it's talking about half an amp. That's not a lot of energy. So if you plug in here at rated power, that's 2.5 watts in, and you're getting what, like 1.7 out? So you're losing 0.8 watts. If we're talking about our motor controller, which can put out several kilowatts, I don't care about this. This is stupid. So that's why we might use a linear regulator for that part. However, like we talked about, thermal is also an issue. So if we tried doing 3.3 volts down to 48 volts and say, oh, we don't care about the losses there, you're going to have to dissipate many, many watts of heat. And you really can't do that without heat sinking, and you don't want to waste, you know, you're saving money right here. It's the whole point of using this. If you start heat sinking, you're getting complexity. You're really having issues with your costs now because now you're paying for big hunks of metal. So you're giving up your advantages. You don't want to do that. And instead, you use a buck converter. Buck converters, they are more complex. They do have more noise. They cost more money. But this is what makes up for it. Their efficiencies are incredible. A very good buck converter can be 97% or higher. The very, very high-end ones can get to over 99% efficiency. And then some of the cheaper ones we might use here, again, this is a lower power buck converter. We might use this to step down from 48 to, let's say, in our case, like 12 volts. That one is going to be more like 85 because we're going to give up a little bit of efficiency and we're going to cut cost. Maybe we're not going to get a huge inductor. Maybe we're not going to pay for like the fanciest capacitors and use some cheaper ones. So that's why you might see some lower efficiencies, but that's going to help bring this high cost down closer to your linear regulator. And again, the main reason I suggest using these is high power or high voltage difference. There's no reason to use them for little voltage steps. It's just more of a pain actually. And for example, for our motor controller, get off this here. We actually, so we have our, right here is where our buck converter lives. And this takes in 48 over here. I'm gonna clean this up real quick. So we have 48 here. And out here, it's putting out 12 volts. And what happens is this kind of wiggles its way over here. And right here, this is our linear regulator. And that's stepping from 12 to 5 volts. And that feeds another linear regulator here that puts out 3 volts. And this part here might only consume half an amp. So if we look at our losses, they're not that bad. And as you see, this is even quite a beefy part here that can actually do some serious heat sinking to help deal with those thermal issues that I just mentioned. However, if we went straight from 48, it'd be too much energy. Also, this kind of splits off, and this is feeding the things we don't care about. These are our gate drivers. They don't care about how clean their power is. They're fine with that. So that's why we're gonna have the buck feed them. However, you have this microcontroller there, which is super sensitive, and it's going through the work of taking those analog measurements. So if you have any noise feeding this, it's going to mess up your control, which is why we use the linear regulators to feed this part. Let me get off that real quick. All right, that's it. Let's go back to Q&A. So Skylar was asking about general design. Skylar, could you add any more to what your curiosity was there? Is he still with us? Okay, yeah, so you want to talk about kind of the intuition from yeah, so if you want to get your feet wet, my favorite thing that I would suggest is never really build a buck converter from scratch unless you have to. So right here, this is my go-to buck converter. I love this LM5017. If you look at the boards that on our team, you've seen these just about everywhere. So what I'd suggest is maybe play around with implementing this. So TI actually, in their data sheets, they're amazing. I'll pull it up. They walk you through how to implement every part of this and explain where all the math comes from for how to go through implementing one of these. So maybe taking a crack at building one of these might be a nice start. Because what happens is, the really nice thing about the LM5017 is you don't have to worry about all these separate parts together. They're kind of all baked in. Okay, let me get rid of that little thing before it drives me nuts. So here we see this is a much simpler design. The one I showed you is like that's the LM17 implementation we use. Start with a simpler version. So right here, this is just how you turn it on. It's literally any value resistor. This is how you can do some lockout. So if you don't want the buck converter to turn on, they go through the math on how to keep it off at low voltage, and only when the voltage is the right, it comes on. And then this is where you're gonna start applying some of the math we talked about. This is your input capacitance. So this is where you're gonna take the math we just mentioned and apply that there. Here's your bootstrap. Now we can't use the 10x rule for this one because the FETs are baked in here. So this is all secret sauce. However, they tell us what this is. So this is actually a 0.01 microfarad capacitor. So from that, we can actually infer that the gate capacitance of the FETs inside are roughly 1 nanofarad. And then again, you're solving for your inductor here that we talked about. So this is more applications, getting a start with it. And then your C out. I want to mention this here. So they call for an external resistance. Like we talked about, there's zero parasitics. To help with some stability, sometimes they want an RC here because it helps their feedback circuit. I'm lazy. I don't do it. I haven't noticed any issues with it. I'm sure there, whatever secret sauce control theory they have prefers this. It's not a big deal either way. So I don't actually suggest trying to play around with it. And then another tool that you can start with is if you're really lazy, and I really don't suggest this, but you can use something called WebBench instead. And this is kind of, I just want the solution. I don't care about the problem. And oh, wow, okay, don't use this. Apparently, it doesn't even load right now. But if my internet was working, basically all it is you give it its parameters and they will straight up tell you, here's what you use for L, here's what you use for C. So they're making the assumptions for you instead. But here's an example of like a starting point I suggest. If this is maybe a little too easy and you want the external FETs, you can instead switch to other TI parts where they're going to have the external FETs, so you can choose those as well, you know, play around a little more. But there's a good way to start. All right, other questions? Because I know I ran through fast. The motor controller is going to have more discussions into this as well. We're going to talk even more about kind of the application. This is more just, I wanted to get the theory out there. So the motor controller lecture isn't as much as like a huge wave.
I don't know. Everything was good.
Yeah, and then also feedback. This was like a first shot at doing these. Was it too much math, not enough concept, not enough application? I know Skylar seemed more interested, like I should throw a little more application.
I don't know, it was good for me, but like also I was working on this stuff, so.
Yeah, and that's the hard part too, is like we have a lot of members at different stages. And
Yeah, and also our lecture is recorded, Skylar. Yeah.
yes, the whole thing's recorded. God, I hope so. Yeah, recording on this computer, good. Nope. Well, I hit my hour target at least. In terms of feedback, is this the right length, too long, too little as well? I don't know how people feel about that.
It was great for me, I don't know. And
I
I
think
was
this is a
great.
pretty good length.
Yeah.
Good.
Yeah, I think so.
All right. Yeah, Skylar, I'm gonna try to do these every week. We have a list of topics we're looking at, so we're gonna start with power electronics because this is something I know more off the cuff, so I can make these easier as I try to kind of find how I want to shape this format, so I can make them more rapidly and kind of play around more. And then we're gonna kind of switch after we're done with the motor controller into laying some software work. So we're gonna talk about interrupts, talk about how the microcontroller programming works. So yeah, that's where we're gonna go next. And then last, we're gonna talk about batteries once we're done with our software session. So yeah, interrupts are really cool. 391 makes them kind of scary because they go into the real nitty gritty. But the reason why we use STM is because the software is so clean and we're able to kind of at an application level work with interrupts rather than at a bitwise level work with interrupts where that's where the pain really is.
Fuck the IRADs. IRADs don't work.
Yeah, I'm sure 391. No, wait, you finished 391, right, Dimitri? You did that last semester?
No, I'm taking it right now.
Oh, you're taking it now. Oh God.
Yeah.
391. I'm sorry.
Yeah, it's fucking, yeah.
You can't even check if your thing works on their computers.
Yeah, whatever. It's fine. I have smart guys in my team.
Yeah, that's definitely what I relied on.
Yeah.
All right. Anything else? All right. Cool. Thanks, guys.
Mhm.
I'll clean up the recording so there isn't the very long silence at the start, and then I'll post it to Google Drive and drop a link in the chat. All right.
Thanks.
Thank you.
Well, thanks.